everybody. So yes, as Ben was saying, this is kind of the first in the series. One of the areas of microsystems that we're interested in highlighting is, of course, microelectronics as a system in the context of instrumentation in solving biological problems. And so I'm aware of some colleagues of mine, Leonardo and Reid Harrison, who've been working together with a number of other colleagues in this area of neuroscience, where you're trying to build some extreme instrumentation to be able to measure something about biology, neuroscience in general. So we brought them as a joint talk, which is rather unusual, but mainly because they've been working very closely together to bring a biology perspective and the experimental work perspective together with the technology to build more of an optimal system that you wouldn't get if you don't have both sides together at the same table. So I know Reid Harrison and Anthony from graduate work at Caltech. Reid has a BS in electrical engineering from the University of Florida, where he worked on some mobile robotics, where I got to know him as he came into the PhD program at Caltech in computational neural systems. He worked on models, VLSI circuit models of fly visual system and sensory motor processing, and has been at the University of Utah in electrical and computer engineering, in bioengineering and bioengineering. And he this year left to focus on his company, Intan Technologies, which is up there. Anthony Leonardo he has some cognitive science, Carnegie Mellon, and focused on artificial intelligence and neural systems. He went to Caltech to work on a PhD in Mark Konishi's lab, where he really jumped into neurophysiology in zebrafinches. He did a postdoc with Michael Fee to work on more technology related to recording technologies, and is now as a group leader at Janelia Farms, which is a Howard Hughes Medical Institute campus out in Virginia, so he's local. So I will hand the floor to you guys.
Okay. Thanks, Tim. Can you guys hear me? So thanks for having us both here. So as Tim said, the talk will be a little bit unusual, but it reflects the unusual nature of our collaboration. So first, I will describe to you in introductory format the sort of common problem that has interested Reid and I for the past few years, the problem of trying to record wirelessly from Dragonfly neurons while they're engaged in a complex behavior. So I'll sort of try to give you a sense of why that is a scientifically interesting problem within the field of systems neuroscience, and what the technical challenges are and what we hope to answer. Then Reid will talk and give you the sort of general purpose solution to that problem, and then I'll talk again at the end and sort of tell you the specific enactment of that solution in the context of this problem again, and what we have to do to put all the pieces together. And so with that, let me get to the beginning. So, okay, so here is a dragonfly. Small animal, weighs about 1/2 gram. Up here you see a fruit fly. And so if you watch this dragonfly, you'll see it take off in the air, catches fruit fly in midair, right about here. Pulls a very fast 7G turn. So I'll play it one more time so you can kind of catch the whole flow. So this little moving speck is the fruit fly. And so dragonflies make their living doing this behavior over and over again every day. They do it about 100 times per day. And if you look at this flight very carefully, you see that what the dragonfly does is it starts from a stationary position and takes off, and it never flies right at the fruit fly, but it calculates an interception course and moves itself downstream in real time using visual feedback to figure out where this prey item is. And so the question we would like to understand is how is that done? Let's see if I can operate this from back here. Okay. Danger. And so, okay, so here's a few so we filmed these foraging flights at about 1,000 frames per second. And so here are a few still sort of frames showing the time varying position of the dragonfly roughly every 20 or 30 milliseconds in the fruit fly. And so matched time points are shown in the same color, and so as the colors get brighter, time goes towards the end. And so here's sort of 3 different foraging flights. Okay, you can see in every case the dragonfly takes off, it's in some random orientation, it sees the fruit fly, and it always flies in this sort of triangular interception course, right? Its body is never pointed at where the fruit fly is at the same time point. And sometimes these flights of the fly are very complex, not because of evasion, but because the fruit fly is diffusing through the air and it has some turning probability. And you can see when the fruit fly turns, the dragonfly makes a match turn sometime later, and these flights can be very long and very short. And so the question is, well, how exactly does the insect, the dragonfly, solve this problem? So we've started doing very quantitative studies of prey capture. We have an indoor flight arena we've constructed where dragonflies start from a controlled perch. They take off they launch themselves in the air after fruit flies in free flight. We film them with 2 high-speed video cameras, and then we reconstruct these 3-dimensional flight trajectories. And then we can ask very interesting questions, primarily about what are the guidance laws underlying this behavior. And so if we look at that, now I'll just give you a rough flavor of what is the rough statistics of this behavior, okay, the first order statistics. So here we can just look at distributions of flight times, so the time from when the dragonfly takes off to the time when it catches the fruit fly in its legs, and it's a basket out of the leg. So we can look at things like flight times, flight duration, number of wing strokes, and these distributions are all very correlated because they're related to each other, but what we see is the average flight is about 1/3 of a second long, 1/2 meter in distance, 14 wing strokes. So in other words, over this 300 millisecond period of time, the dragonfly goes through about 14 motor states. He has 14 strokes of the wings to keep himself guided on this interception course to catch these fruit flies. Now, what does speed and acceleration look like? We're in a free field, so our fruit flies are flying at about 1 meter per second. They turn but rarely, so they're kind of going on a roughly straight course. The dragonfly, in contrast, starts at a stationary position. He's not moving. His speed ramps up over the time of the flight, and so by the end of the flight, he's going at about 2 meters per second. This, of course, happens at 300 milliseconds, so they're accelerating very, very quickly. If we look at distributions of accelerations, you can see that these dragonflies, on average, are flying at about 2 or 3 Gs, but their flights go up to 6 or 7 Gs. The fruit flies are a factor of 2 or so below, and this is all sort of what we expect from basic requirements of catching them. The dragonfly has to accelerate substantially faster than the fruit fly. Now, if we look at these flights, these interception flights, what you notice is that they very much look like the paths of a guided missile. So here's our fruit fly, here's our dragonfly, and you see you get this triangular interception course, and here's a guided missile being launched in some hapless airplane. And you can see these things, qualitatively have the same feel, and so it leads one to sort of say, well, what guidance laws does a missile use? And is there anything we can learn from those formalisms that are relevant for dragonfly foraging? And even if they're not relevant, it might point us to interesting questions. And so how does the missile work? And so the way the missile works, in most cases, is with quite an ancient guidance law called proportional navigation. And so this is the same way sailors and ships avoid hitting each other, and many of you are probably familiar with it. And the idea is quite simple. We have a fruit fly at some point in space. It's moving with some velocity vector. It has a bearing pointed this way. Our dragonfly somewhere else. He has his own bearing. And so the dragonfly measures the line of sight from the horizon to himself to the fruit fly. So we'll call that lambda. That's some angle. And so if the fruit fly is moving at a constant speed, constant velocity, the dragonfly simply holds this line of sight angle constant at every time step. And if he does that, he's guaranteed to catch the fruit fly. Okay, so this is what the sailors do. You look off the bow of your ship, and if you see another ship, some angle with respect to you at time t1, and then 10 minutes later, you change course because you know you're on a collision course. Now the question is, what happens if the fruit fly changes direction? So here's such an example. The dragonfly is here. You'd like to see this line of sight angle, but instead the fruit fly has moved, and so you can see there's some air angle. There's a drift in the line of sight angle you would like to see. And so the dragonfly measures his derivative, and he applies an acceleration to his own course proportional with some gain to the drift in the line of sight angle. So here we get a drift to say 1 unit, and he does a 3-unit change, so that's the gain, and he then recovers the interception course. And so this is just the formalism of proportional navigation. And so we can ask the question, does a dragonfly do anything like this? And indeed, it seems they do. So here we plot these line of sight angles for elevation and azimuth, and they're slightly different, so I'll tell you about them in turn. For a dragonfly, for maybe 100 canonical flights. And so time 0 here is the time the dragonfly takes off. And this is going forward in the foraging flight, so 300 milliseconds is the typical length of a flight. Of course, in practice, many are longer or shorter, and so we just cut it off here to give you the flavor. And what you can see is there's some mean line of sight angle and elevation of about 65 degrees, and any instantiation of the trajectory wobbles around that, but the dragonfly actively stabilizes it back to this angle. So if you follow any one of these paths, you can see it goes down, but then invariably goes back up, and so you have a mean angle of about 65 degrees in elevation. In azimuth, we see something a little bit different, but fundamentally the same in terms of using an error signal based on visual angle, which is the bearing between the fruit fly and the dragonfly. Start off at some random state, so it's somewhere between plus or minus 360 degrees, but the dragonfly stabilizes this to 0. So in other words, he likes to go in the same direction of the fruit fly. And so from here we see the canonical way these foraging flights are made, which is the dragonfly comes from behind, from below, and upwards at the fruit fly. So you never see flights of a head-on collision, so to speak. The dragonfly always flies to behind the fruit fly and up at about a 65-degree angle. And so that's interesting. This is sort of effectively the visual blind spot of the prey. It's hardest to see, and the dragonfly is able to accelerate on it on a very fast interception course. Now, this is a qualitative description, but which we could apply in a more strong formalism and ask, is this complete proportional navigation? Is it related? But instead of doing that, let me tell you a little bit about what's under the hood and how we can test these ideas quantitatively. So here's a dragonfly. If you look very closely, here's the compound eye. The top or dorsal surface of the eye points up at the sky. That's this red blob. The brown part is the ventral surface of the eye. It points downward. And if we look in the neck connective, in the spinal cord, so to speak, we find a set of axons which contain these so-called target-selective descending neurons. So it's a set of neurons discovered by Rob Olberg, a good collaborator of mine, and these neurons have the compelling property that they respond only to little moving targets. So if we put a target on a screen and move it around like this, and our dragonfly watches the screen, and we have an electrode here in the neck connective, these neurons, every time the target repeats its trajectory, which is a row through this little matrix, these neurons fire a spike at the same time point. So they respond to little moving targets, and if we stimulate them electrically, the wings twitch. So they are a sensory motor bottleneck. They respond to visual targets, and they alter the state of the wings to effectively steer the animal. Now, how does this tie back to our proportional navigation story? Well, if we look at the receptive field map for these target-selective descending neurons, of which there are only 16, they wrap around the animal's head with a center point at 0 degrees azimuth, roughly 60 degrees elevation, and they have direction selectivity in different dimensions. And so you can see it corresponds coarsely nice to these, it responds approximately to the angles we show here. So in other words, the dragonfly, we think, tries to hold the prey stable on his visual fovea of the compound eye, and as it drifts around in there, he gets motion control signals from these neurons that steer the wings that cause him to resume this interception course. So we think, we hypothesize, these target-selective neurons effectively implement a guidance control like proportional navigation. And the question is, how can we show quantitatively that that's the case, right? And so we have a circuit where the target flies around, these neurons detect it, they convert that into steering signals, it alters the dragonfly's position in space, that feeds back, he sees the target somewhere else. And so to really understand a circuit like this, we need to measure kinematics, we need to measure positions of these animals, but we also need to record from these neurons in the flying insect, because the studies we have so far are all in restrained insects, so there's no motor control anymore, and it's very difficult to make any statements about how these guidance laws are implemented. And so therein lies the collaboration Reid and I have started, because fundamentally we need small, lightweight electronics to study these things. And so now I'll hand it over to Reid.
Yeah, thanks. And Anthony will be back to conclude the talk, actually. So, yeah, you can see here what we typically find in an electrophysiology lab or neuroscience lab that studies the electrical property of neurons. You see a lot of really big, bulky instrumentation that is there to amplify, filter, and record the weak electrical signals that you record that you can sense in your neurons. And all of this is nice equipment, but it's not amenable for neuroethology, studying behavior, especially in small animals, because it's just large and bulky and not portable. It would not fit on the dragonfly.
We've tried that.
We tried that. We won't show the video of that. So in an effort to miniaturize a small version of what I just showed you, I'm an analog IC designer, a chip designer, and so we developed a telemetry chip, which was, this is a photograph of it. It was less than 3 by 3 millimeters, fabricated in a fairly inexpensive 0.6 micron process. And it contained a number of things I'll be talking about just briefly, The first was low noise biopotential amplifiers that were optimized for a particular neural signals. This particular, well, I'll say a little bit more about them later, but we amplify the electrical signals that we get from electrodes. We digitize them with a 9-bit A to D converter, and then we transmit them using a 920 megahertz oscillator and an RF amplifier. And then we have a crystal oscillator so that we can attach a crystal, and that gives us a very well-controlled sampling frequency for our A to D, so we sample them at a known rate. So yeah, we transmit FM, but we transmit binary FM, frequency shift keying. So we're transmitting digital data by alternating quickly between two different frequencies. This is 2.6 by 2.7 millimeters. That's just the chip. There's a little bit of extra stuff that we need to make this work. So just a couple of slides on the circuit stuff. I'm not going to get very deep into this, but the front-end low noise amplifier is of a type utilizing operational transconductance amplifiers and special feedback elements that we've published in a couple of papers from the last few years. And the bottom line is we've figured out design techniques that allow circuit designers to optimize for a noise-power trade-off. If you want to push circuit noise down so that you can see very small microvolt-level signals here and neural signals on the order of 100 microvolts, then the circuit really can't add much of its own noise, but all physical devices add noise. And it turns out when you try to push power down in circuits, you do so by typically raising the currents that the chips draw from the power supply. And there's a trade-off, and we've found ways that you can get within a factor of 3 or 4 of the theoretical minimum of this. So you can exercise this trade-off as well as you can. And so we design a higher gain of 1,000 for neural signals, a lower gain for EMG or muscle signals, which are larger to begin with. And then for the frequency shift keying FSK transmitter, we have an on-chip inductor. That's what you saw a couple of slides back in here. These circular things are just round coils of metal on the chip. We have a process that has a thick metal layer option, which is really nice for designing low resistance inductors that have high quality factors. So this is an inductor, and the capacitors are here. And with that combination tuned to the right frequency, we can have an RF oscillator that oscillates at around 200 megahertz, but we use MOSFETs as variable capacitors, voltage controlled capacitors. And these would be the digital signals coming in from the A to D converter with the data from the spikes from the neural amplifiers. And we modulate this, and that shifts the frequency here a bit. And then that is passed through a simple RF amplifier here to a dipole antenna off the chip. We use, in this process, we had fast bipolar transistors, which we used here, NPNs at least, to give us a high transconductance to current ratio and low parasitic capacitance. And so we could operate this thing for well under 1 milliamp. And a thick metal was used to build a low loss inductor that had a Q of about 11 at the operating frequency. So that's how we build the FM transmitter. You notice it is an open loop transmitter, which means that the frequency is set by this inductance and this capacitance. And so it's susceptible to temperature drifts, and also if the power supply changes, the frequency does drift. Which means that it can be a bit troublesome to receive the signal. You have to sort of track it with the receiver by hand. But if we add a phase lock loop into this to synchronize this to some multiple of the crystal frequency, we're investigating that now, but all the solutions consume a considerable more amount of power. And so we're also concerned with battery life. But this is a block diagram of the system. 2 EMG signal amplifiers for muscle signals, 2 neural signal amplifiers. They're multiplexed in with also, we have 3 inputs to the chip that allow us to use a commercially available MEMS accelerometer from analog devices. This is the little thing in the Nintendo Wii hand controller. You can get it for like $10, and they have X, Y, and Z acceleration, plus or minus 3 Gs. So in the first version, we included one of those. They're digitized, and then they're sequenced into the oscillator and then transmitted out. Now, power is a concern in all of this. this is just another picture of the chip, so you can see how big the chip is relative to the canonical finger. And then we often package the chips in this very, very small, what are called QFN packages. They're industry standard plastic packages called quad flat pack, no leads. And this makes them a little bit bigger and quite a bit heavier, but it's easy to assemble on boards that way. So power is a challenge in all the circuit design because small batteries have a limited capacity. And this is the battery we're using. It's an Energizer 337 zinc silver oxide battery. We investigated a lot of exotic batteries this size costing $40 from Swiss companies. We finally found the best performance from a $2 watch battery made by Energizer. But the nominal voltage is about 1.5 volts. And this has the data sheet tells you it's rated with a capacity of 8.3 milliamp hours. And you go, great, if I pull 8.3 milliamps, it'll last an hour. Well, the trick with all of these tiny, tiny batteries is that they evaluate them at the kind of current levels that watches draw, or hearing aids draw, which is about a microamp. And at a microamp, you can get 8.3 milliamp hours out of this. Once you start pulling higher current levels, like the roughly milliamp we would need, actually it only lasts 3 hours. So it's, and in fact, if you try to pull a mere 5 milliamps, the voltage immediately collapses to 1.2 volts and dies within a few minutes. And you can see how much the voltage sags and the lifetime is shortened at these fairly modest current levels. So you have to actually characterize the batteries or power sources you're using for these higher current tasks. So this weighs 130 milligrams, and you see the size of it here. So this was our first version of the wireless telemetry backpack. It has the packaged chip in this QFN package, and then 2 batteries because we designed a 3-volt chip, and the accelerometer that we used could operate at 3 volts and could actually not operate at 1.5 volts. You can't find a MEMS accelerometer commercially that operates at less than 1.8 volts, so you need 2 of these batteries if you want to use an accelerometer. And there's a crystal and a couple of little off-chip surface mount components, but that's the size of it, about 13 by 9 millimeters. And it weighs about 1/8 of a gram. So as a point of reference, a business card weighs about 1 gram. So this weighs a little bit less than a business card. It pulled about a little less than a milliamp, which gave us a battery life of 2 hours. These are the things that it could transmit, about 2 meters. Neural channels sampled at a barely acceptable sampling rate. EMG channels sampled slower because they're lower bandwidth, and acceleration channels sampled fast enough that you can actually see wing beat accelerations. So we are limited in the data rate we can send, mostly by the availability of commercial receiver chips. We didn't want to build a receiver from scratch, and it's hard to find receiver chips that go over. What we have is about 350 kilobits per second. Yes?
Reid, how much does the Dragonfly weigh?
The dragonflies we're using, which are medium size, not the giant ones you sometimes see, are about 400 to 500 milligrams. This was actually designed first, and maybe the next one, we'll get to that, but this was designed for a locust, actually, which is 2 to 3 grams. Yeah. So these were connections that you solder little wires to, just touch and solder quickly wires for the neural channels, and we built a custom receiver to connect to a PC with a USB interface. We have a question. Yeah.
So how long, so that's a half dipole?
Mm-hmm.
Is it actually quarter wavelength?
No, it's less than a quarter wavelength, so we're not anywhere near 50
Wavelength.
antenna. Wavelength for 900 megahertz is about a foot. So yeah, we were using a suboptimal antenna too. It would be nice to go to 2.4 gigahertz or something, but then you're but yeah, somewhere that's free from cell phone interference and things like that. But one thing that's nice about 900 megahertz is it's actually a very, very quiet band. Almost all the consumer electronics has moved up to higher bands, but yeah.
So I've heard that lead solder can have significant weight adding emissions.
I'll show you the weight breakdown later. We got all that, yeah. So we actually first started testing this in a project with Fabrizio Galbiani and a couple of his students at Baylor College of Medicine to study a cell in locust or grasshopper that actually responds to visual looming targets. So a grasshopper is sitting on a leaf and a bird is swooping down to eat it. And what happens is that the image on its eye grows larger and larger and larger, and it perceives this looming stimulus visually. And this cell called the DCMD starts spiking faster and faster and faster, and then at a certain point it jumps. And the spike activity actually peaks before the jump. This is a visually mediated escape response. And it's been very studied in, of course, fixed animals. And the behavior has been studied without seeing what's going on with the neural behavior simultaneously. And we wanted to, for the first time, study both at the same time. So we instrumented a locust with this first system. We also, there was a lot of extra weight for connections and things like that. We didn't have the electrode connections down just right. There's a battery on the side, waxed to the insect with beeswax. And then, let's see. What you'll see here is a video of, okay, so the insect is actually, is free to move. It's crawled out to the end of this little stick that's in front of a computer monitor. And so you're going to see a computer-generated image right behind it of a simulated sphere or circle approaching it on a collision course. And what you're going to be hearing now is the neural data that was recorded from one channel from this DCMD neuron.
You're on the leg. You're on the muscle.
Oh, I skipped one. Thank you. Yeah, great. So I'll play this a couple of times. So that was about a 14G jump. Our accelerometer is saturated, but it's a very, very fast jump. So that's the first time that we've been able to actually monitor neural activity in a real behaving animal, and it turns out that the neural activity is about twice as active as it is in animals that are held down and can't jump when you're looking at the same neuron. So that's interesting. At the same time, same experiment, we were measuring two EMGs, one from leg extensor and one from leg flexor muscles. This is the EMG information from the leg extensor muscle. And you heard it happen before the jump, and that's because it co-contracts flexor and extensor and basically energizes a spring and then releases that spring to jump at a certain trigger point. But you see it was completely silent until a certain point leading up to it, and then you hear the co-contraction. And that's when it's decided to jump, essentially, at that point. So this shows some of the data we've gotten from these experiments. This is being published very soon in the journal Neurons. We have, when the stimulus grows, the DCMD neuron becomes more and more active. The spikes actually do get physically larger, which is kind of interesting. It's not an artifact. And then you can see the EMG activity in the leg as it stores up energy in preparation for jump. And this is kind of cool. The Z acceleration, you see this level is different from the level after the jump. That's because this is 1G of gravity when it's sitting on the ground, and after it jumps, it's in free fall in a ballistic trajectory, so it's 0 Gs. You see it on the X and Y channels as well, I didn't show.
Those bigger spikes are probably different muscle, okay?
Well, this is from the nerve cord, so it could be some kind of contamination with a nearby muscle. It could be. Yeah, it could be, because this is just a hook around an entire nerve cord, and the DCMD is usually the largest signal you see.
So I want to make sure I understand. This is actually hooking the entire axon. So you're getting a compound action potential. But you're really looking at the biggest spike that occurs there normally. Which
Right, we're hooking a nerve cord that has dozens of axons.
But do you know for a fact that, I'm just curious, do you know for a fact that the spikes that you're seeing are DCMD?
Based on many years of historical experiments, yeah, the biggest one always, it has the largest axon, so its signals travel fastest, since it's obviously an urgent control signal. But we don't know with 100% accuracy, but
I mean, you know pretty much. I mean, the hook you put around the bottom of the cord, that's exactly where the axon lies. So you're physically closest to that axon, and it's the biggest axon, and that's the largest fields. And so, you know, to that extent, I think we're pretty good confidence.
Yeah. So we're just starting to expand these experiments and see, but the interesting thing is that we are getting quantitatively more spikes, significantly more spikes, more activity when the behavior and when the neural activity is measured coincident with the behavior, not just the sensing, as was done with animals that were sort of tied down. So we've also started flight experiments with a wind tunnel. This is a low-speed wind tunnel that gives a nice laminar flow at typical locust flight speeds. And the locust is positioned here in the middle, and it hangs from a little string to keep it from banging into the sides of the wind tunnel. But basically, we can attach it with a little magnet to a string and a counterweight, so it can fly up and down. It's sort of a string with a counterweight. And as it flies, we've actually been able to wirelessly record. This actually shows our MATLAB GUI. As the insect is flying, we have it on a video camera here, and we're seeing neural, well actually this is EMG data. We didn't have the neural electrodes hooked up here. We're seeing acceleration and EMG data here as the experiment's going on. And yeah, it actually is. So the amplifiers are pretty low noise, and then the electrode placement was very good in this experiment. So this shows this is the animal was just hanging and it wasn't flying, and then when you start wind blowing across it, it starts flying. And so this is right and left wing depressors. You can see the electrodes were probably placed different relative to the muscles here because the amplitude's different. But you can see the body actually start to accelerate as the wings start beating, and you can probably achieve some sort of mechanical resonance in the body. So this is just some preliminary experiments. We're going to be recording from DCMB as looming stimuli are projected to the wind tunnel as well. So that was preliminary experiments with locusts, which are bigger, heavier animals. On the version 1 system, working with Anthony, we also used it to record spiking activity from a motion detection neuron and Dragonfly nerve cord, and we recorded the same activity using a commercial amplifier and the wireless telemetry system. So you can see that we're really the wireless telemetry system is giving us data at the same, roughly the same quality level as a commercial system, big boxy plug-in-the-wall system. So this was still too large to fly on Dragonfly, however. So we went to a next generation telemetry unit, version 2 chip, which we just call Bug2 for short, was designed in a smaller 0.35 micron process and had lower threshold voltages, so we designed everything to work at 1.5 volts. So we could run it off with a single battery instead of 2 batteries. And that eliminated a lot of the weight. And we had to eliminate the accelerometer because of the lower voltage, but with a lot of the video tracking that Anthony's doing, we don't need the accelerometer so much. So we actually designed a chip so that the only thing that you have to attach to the chip is an antenna, a battery, and a crystal, and that's it. And it was in a smaller package as well. The battery is connected by actually soldering a couple of wires. You can make it so you can tap solder in place when you're ready to start the experiment. And then you solder on wires for all the electrode signals. But again, you can just solder with a quick tap, so it doesn't heat up regular silver. Yeah, silver solder, lead solder. Yeah. And this drew a little bit less current, and so partially because we don't have the accelerometer, and so it lasts for 4 to 5 hours with one battery. And we'll eventually figure out this thing. The breakdown by mass, this shows the very first system that I showed you, how much weight is consumed by battery holders, the printed circuit board, the accelerometer. Well, we went from 2 batteries to 1 battery. We went to a smaller circuit board. This is a 0.5 millimeter thick circuit board. It's still a rigid fiberglass circuit board, and lost the accelerometer. We were able to get the mass down quite a bit. This other timber includes the solder, so it's not too much of a problem. So we were able to get the mass down to 280 milligrams. But as I said, we're working with small dragonflies where that are only weigh 400 to 500 milligrams. So we had to actually go further and be more aggressive in reducing the mass. And so Anthony's going to conclude the talk by talking about that, and we can both take questions at the end if you have any more questions on the chip stuff.
Okay, so as Reid said, so here we've got the chips, and these really, from the locus recordings and similar noise, solve the problem of wireless transmission. And the question is one of sort of packaging and systems integration. How do we put it on a Dragonfly? And of course, with the locus, I think everything works well. And so it's really, what I'll tell you now is very specific to a specific application, but it's perhaps pedagogically interesting is the steps we've needed to take to actually now apply this very powerful technology to a specific question. And so the first question is just, well, how much can a Dragonfly carry? And so here we've done a lot of tests of lift, how much mass can a dragonfly hold. And so here's sort of a simple video showing the results of that, where we have our fruit fly flying around. The dragonfly is watching him. And so this dragonfly will take off in a moment, and it's carrying weight. And you'll see this sort of little payload it's got under its belly. Right under here, you'll see a little shiny thing. It's just a battery, but it weighs about 130 milligrams. And so we can do studies like this where we examine the dynamics of these foraging flights with added mass and ask, is the dragonfly still doing the same thing? And so through that, we can figure out how much can we put on. And this is about how much we can put on. 130 milligrams on a roughly 450 milligram animal, or in simpler terms, about 30% body weight. So that is our cutoff. And so if you watch this, well, it's a little hard to tell from watching this, but the behavior is certainly effective. That's the first question people ask me. Is anything different? And of course, if I throw a third of your body weight on you and ask you to play kind of high-performance football, it's a little bit harder to do things. So the dragonfly can't accelerate quite as fast. It's harder for them to catch things, but they still forage successfully. They still can eat and maybe not gain weight as quickly as they can, but they do okay. So we think the essential dynamics are intact. And so the question is then, how can we build a telemetry system that weighs 130 milligrams or less? Okay, so here's where we were sitting. We started at 800, which is really way too much. We're down at 280, and the question is, where is the sort of sweet spot for miniaturization now? And so reducing the batteries is a crucial thing. That strips off a ton of weight. But there's another very simple thing we can do, and that's move from a printed circuit board to a flex board. And so here's an example of such a flex board. So this is just a Kapton dielectric. It's about 25 microns thick with copper pads on it. Here's our, rather than having a packaged IC, we have the raw die wire bonded onto this flex board. And so this in and of itself makes a tremendous difference. The weight of the PCB and the packaging for the die is on the order of 120, 130 milligrams. This takes it to about 6 milligrams. So you save a huge amount of weight right there. And I think we have a slide. So this gets you from 280 down to 172. And again, in doing this, one question you asked was about lead solders, and all those little bits of weight on a preparation like this add up quite a bit. So we generally, will reflow solder the standalone components onto the board, but then electrodes and other things will hook up with silver print and use adhesives to seal that on. And that, I mean, with solder, you can easily add 20, 30 milligrams of weight to these boards, which is not a lot for some preps, but for us, that's now a significant fraction. Use a silver print, a conductive glue, and then you put a polymer on it, like a light cured polymer to make it hard. Another nice thing you can do with the flex board is, since it's so much lighter, we can stick a regulator on the back, and that makes the transmission frequency considerably more stable, because now the battery, which wobbles around a little bit, is locked to, say, a volt and a half. So that gets us down to 172, but the question is, how do we go further? And at this point, you can see we really would be hard pressed to change any of the components other than the power. The power is the fundamental thing. It's taking up 3/4 of the mass now. And so the problem for us, if you think about it, is the battery is wonderful and it gives you 5 hours of life. But if you look at the foraging flights I told you the average flight is 1/3 of a second long. And a typical flight, if we want to let the dragonfly look around a little bit and then take off, and then you can glide back down, in the upper bound, that's 5 or 6 seconds long. So we really don't need 5 hours of flight power. We need like 5 seconds of flight power. Now, how could we produce that? Well, if we take, for example, a supercapacitor, you can actually put enough charge on a supercapacitor to get reasonable amounts of power. So a 30 millifarad supercapacitor will give us 20 seconds of power, and it will let us go from a battery, which is 130 milligrams, to a supercapacitor, which is 30 milligrams. So it saves us 100 milligrams of weight, but that would require us instantly charging it and getting a flight and getting the animal back down. So the question of going to a rechargeable power supply is just that. How can we recharge it? And the way we do this is with an array of photodiodes that can actively charge when the animal's on a perch. And so here is the sort of backpack that we've been using. So the original flex board with all of the IC remade, the voltage regulator, the antenna, etc. That's all of this little board here. The contrast is a bit hard to see. Here's our supercapacitor, which is supplying power, and underneath this is a second flex board with an array of 6 photocells on it. And so you can see the circuit is very simple. We're going to do something to charge up the photocells. They charge the capacitor. That sends power to the regulator. The chip runs.
So there's a regulator coming off the supercapacitor.
Yep, yep, exactly. And that's crucial, of course, because now instead of with your Energizer battery where you wobble a little bit about 1.5 volts, here we're going to charge up to say 2.5 volts and drop down to 1.5 volts. So without the regulator, you're sort of dead in the water. But so you need it for that, but it also gives you, I think, a little bit more stability over the battery. And so the way we charge this thing then is, so here's a bottom shot. You can see the little photodiode array. Okay, so this is everything I showed you a moment ago is on the underside of this. If we can actually go back one, here you can see these very thin silver wires that go into the animal. Well, these are sort of hookup wires, 70-micron hookup wires, contoured against the size of the animal's body to go into the little patch of cuticle between the legs where we access these neurons. Now, okay, here's the supercapacitor. And so then the way we use this in practice is we charge it with a laser. So we have a platform here. You'll understand in a minute the geometry of this in a live situation, but we have a continuous diode laser here. It's infrared. It pumps light up like this. It gets fanned out. And so if the animal perches here, he gets 25 milliwatts per square centimeter of IR power. The photocells pick that up, charge the capacitor in some tens of seconds to minutes, depending on where it's sitting in its charge state. The thing has enough power, the animal can take off, he flies, he uses his power, he lands again, and so forth. And so that all gets covered up into this nice little package. So here's where the laser light comes out. We've sculpted this very much for the behavior of these animals. So dragonflies, the dragonflies we use in particular, like these little high contrast perches on a background, so they're drawn to perch on this. And so when the dragonfly sits here, he's just illuminated by continuous, very intense laser light. Intense enough, and the delicate balance is you need the light to be intense enough to drive the photocell, but not so intense that you cook the animal. So it's not trivial to do this well, and it's a fine balance. Now, the other thing I'll talk about briefly, which isn't related to electronics per se, but is very much related to getting the signals, is what do we put into the body to sense these neurons? And so we've used a variety of substrates, and ultimately, you know, this is as invasive as putting weight onto the animal. And now we're making a hole in the animal and sticking a probe in, and we need to do that in a way. And you can imagine if you have an F-14 fighter plane and you want to punch a hole in it and attach it to something on the inside, the place where you do that and the manner in which you do it will dictate whether the plane ever flies again. And so it needs to be something very small and non-invasive. And so in the case of our work, we started making these custom little silicon probes. So this is a tiny wafer of silicon. It's got some gold pads etched on it that run down to a reference electrode and a small recording electrode. It's got a little sharp point. And so the length of this sort of sphere, we can customize. We set it to the area we're recording from. So this is on the order of 800 microns long. So if we want to go about 800 microns down, this is what sticks out of the body. This is about a 400 micron footprint. And so you've got a little tiny thing sticking out of the body. Here's a live one. You can see the reference here. And the contrast is great, but there's a site down there. All these recordings, the reason the signal to noise is good in a real animal is because you're always doing differential recording. So you need a very low impedance reference aside from ground to cancel off artifactual motion from the animal. So this is integrated into the probe. And here's actually an example of that silver print contacting these lead wires and going up. So we stick that into the body, and then we can record quite nice signals like this. So this is a but we get very nice signal quality, very much like the locust story. The activity in the nerve cord is completely different in an awake animal, which is interesting. So the whole thing, and it's not surprising. I mean, if you look at the structure of the nerve cord, about half of it's sensory and half of it's motor, and the entire motor half is shut down when the animal's immobilized. And so all that stuff gets active when he's awake on a perch. And so in an anesthetized animal, you have sort of essentially a flat line and then these spikes. And so you have all this sort of presumably motor activity going on in between this single unit, which is an identified target-selective neuron. And so with that, I think we'll take some questions. I'll leave you with the sort of little family of devices that have come out of this collaboration, which are all suitable for different preparations and different experiments. And I think that's about it. So thank you. Yes, this is probably breathing, I think. This was an animal just sitting on the perch, respirating and looking around. stuff. And yeah, so exactly, I think that's motor activity associated with breathing. And one, I think, unknown question that we don't have a good sense of is how good will the signal to noise be in a flying animal where there are many, many muscles doing a lot of, generating very strong fields and doing a lot of stuff, which is very different from an immobilized animal. And this is sort of a taste of it. And I think the hope is that the target selective neuron, you can get very, you get millivolt spikes out of these things. So you can potentially have quite good signal to noise. And I have a sense that that would be a requirement to separate this from muscle activity where, there's going to be a lot going on. So we have to wait and see.
But just to quickly add, another challenge that we're coming up with these with the spikes that you see in Dragonfly is that they're really, really short. They're a quarter of a millisecond. The whole spike, less than a quarter of a millisecond.
Yeah.
And so we're going to need to sample much faster in future versions of the chip so that we can sort different spikes.
Yeah, so we'd love to record 3 or 4 units at once, which you can do in an immobilized prep pretty easily. The axons are close together, but yeah, so there are these very interesting recent observations. People used to do all their preps at room temperature. Spikes are slow. Suddenly, Rob Olberg started warming these animals up to flight temperatures 30, 35 C. The spikes go down to by factor 10. So instead of a millisecond, you have a 100 microsecond spike. And so sorting that at a 10 kilohertz sampling rate and other things is basically.
Just the fact that you cool the animals down and the spikes are
Yeah, yeah. So I mean, one bit of trickery we play with the current thing, which is we have 2 neural channels on there and 2 EMGs, and so we can actually yoke the 2 neural channels together to sort of artifactually double the sampling rate, albeit in a slightly kind of periodic manner. But that's helpful though in getting a little extra bandwidth for sorting. But again,
but you could also use that to cancel out the muscles.
well, we already have a differential to do that, so that we're okay.
But on top,
But you could try to do that as well if you had a real problem.
So most of these neural curves are nerve cores, so from the nerve bundle, it's kind of collection.
Yep.
If you were to try and consider a system like this for, punching into neural tissue,
Like the brain, the head.
the typical
Yep.
ganglia or
Yep.
something like that. So one of the things I don't seem to notice, at least not, well, certainly not this because it's perch, but the movement artifacts we would expect in the flying. Now, I didn't even see it in the locust example. I was a little surprised. Which is all mechanical, I mean, it's 19 Gs.
Well, okay, so I don't know what it's like. I mean, so I guess I don't think you can answer the question of artifacts and TMGs or something. I mean, generally the differential works very well. So, I mean, and I can't say for Dragonflies yet because we haven't done a lot of flight stuff, but let's say in birds where I did a lot of work, I mean, the difference between having a differential reference, a few hundred microns from your recording site, and having it elsewhere or not at all, is night and day. I mean, and the danger is really the amplifier channel saturating before it gets to you, and then you do because you can't do anything. And so, because generally, if you record the full bandwidth, then you can just filter these things off at a very low frequency, so it's saturation that kills you. But if the things are close together, even for pretty big artifacts, we've always had very good success canceling them. And during flight, I mean, during the body moves as although the body accelerates at 5 or 10 Gs, I mean, everything inside it is moving coherently, so it's a very different situation. Like if you have a restrained animal and it's flapping, you see huge movement artifacts, but that's because different parts of the body are forcing against each other. I mean, we've measured kinematics in free flight, and there the whole thorax is moving at a very gentle, low frequency, very small amplitude oscillation, so it doesn't look like, I don't think in free flight the thing is kind of shaking ferociously or anything like that. Tom, do you guys have trouble with the locust recordings in terms of getting signal right at the
No, because you're anchored to the exoskeleton. You wax you've got a really light tungsten wire, that hooks the nerve cord. You wax it to, the exoskeleton.
That's actually stable. Wax not heat. No.
Right, and when these things are flapping, they're really, the locust flapping makes makes a lot of noise, and so there is a lot of vibration. You saw it in the acceleration as well, but we would do experiments for minutes and minutes at least, and never had the electrodes come out or saw serious changes in recording quality.
To get to your question from the head, though, I think recording from the head of Dragonfly is tremendously more difficult than the nerve cord, and the reason is, again, perhaps very specific to Dragonflies, but the head is a very delicate sensory instrument for the animal, so it's attached sort of by a thread to the body, so it acts sort of as a plumb line, and it's got hairs all over it, and it turns, it has kind of 360 degrees of rotational freedom, and so even attaching wires to it to get your signals out, let alone the weight, is something we haven't broached. And then again, the huge issue you have in the head is actuation. You need to be able to isolate neurons by moving them. The whole trick in the nerve cord is you can put in a static electrode and get a good so like these preparations, we go upstairs, we have a rig upstairs, we have these animals chilled, which is sort of our version of anesthesia. We put in these things, we glue the stuff down, and we can hold that unit, the same unit, in the same place with the same electrode after the animal flies around and bangs all other things. And it's basically because the cord is pretty big and the axons are big relative to the sensor size, and so things move around a little bit, but you can kind of hold stuff, and the fields are really big, right? If we were trying to record from a teeny tiny motor neuron, of course that would be hard. But in the head, you have this problem that if you don't isolate, you just have weird hash. And so I think that's like not impossible, but that's certainly something we haven't thought seriously about.
Certainly the difference between motor versus sensory too. Make a big difference. If you're trying to record from the sensory axon, you're likely to get smaller spots too.
Yeah, I don't know. Because of the axon size, I would call this a sensory motor. It's a visual neuron, not a neuron. But so,
So I had two questions. One is, how many axons are in this nerve cord?
I was actually going to show a cross-section of the cord, and I took it out. I mean, so in Dragonflies, it varies, of course, from species to species. I mean, in Dragonflies, there's a few thousand. So, more than 100, but less than 10,000. So it's 3,000 or 4,000. If you look at them, though, it's very beautiful. And I mean, you take a nice cross-section, and you see little circles, and many, a very small number of those circles are very large, and you have the sense that these are very important things. And so all these target-selective neurons are DCMD. So DCMD is actually a homologue of this neuron, the Dragonfly. So these are these huge, very important, very fast-conducting kind of control lines. And so there's maybe 50 of those, 40 of those, and they take up probably a third of the space of the cord. And then the rest of it is very small 5-micron stuff that does all kinds of other motor and sensory motor stuff.
So my question is, after you've gotten those command neurons, the 50 neurons in the cord, are you going to be able, sort of following on what Timur asked, are you going to be able to get
what's next?
information on these small ones?
Okay, so that sort of transcends raw wires. But I mean, for plant, what we would like to do in the short term is so what we would love to do is characterize the dynamics of these target tracking neurons, for which would require the wireless, measure the guidance laws in the animal, think about how the target tracking neurons drive the wing muscles, and we have separate work we do measuring kind of free flight wing and hand kinematics, and essentially show that you can derive the guidance laws from the target tracking neurons. So that will occupy us for many years, right? But if we could solve that part of the problem, then I think the much more challenging problem is to go upstream to the brain and try to say, how do the target tracking neurons get these very compelling computational properties that they have? And so that so we're doing anatomy and physiology kind of in restrained animals that touches on that, and it's not clear if you need telemetry to go into the brain in the sense of if we push that to a sensory problem, perhaps a screen is a place where we can do it. So I don't know the answer, but that's something we think about, but it's a few years at the very least away.
Also, is there only one strategy the Dragonflies use for interception? I mean, if they're tracking other Dragonflies, for example.
That's a very different thing. So when they have territorial patrols,
right.
They have these aerial battles,
right.
And there I would say what they do is much more acrobatic. They do it's sort of a quasi dogfight where they don't actually want to hurt each other, but they sort of want to outdo. So one guy will do some crazy thing, and the other guy appears to try to follow it. Though nobody's, I think, really studied it. I mean, it's very hard to study this quantitatively because there's no way to measure it. I mean, so outside, your camera's never in the right place at the right time, and so you need an indoor environment like the one we've built, but then it's not easy to build that big enough that you get all the territory behavior as well. So ours is kind of around prey capture. They certainly have many different flight modes. In terms of the prey capture itself, I mean, they do, I would say they always do this air angle stabilization. They do it slightly differently in azimuth and elevation, and that's sort of interesting technically. But you never see them kind of doing some totally oddball thing where you say, that's a new algorithm. So it always seems to be, and so it's interesting. It's clearly something that's hardwired. From the first moment you put an adult in, they can do this. They get better at it, so there's some learning on top of it. but it's just something it's something they know, and I think it's physically built into the system in the sense of the fovea of the eye is the coordinate system, and so the measurement of air angles falls sort of trivially out of just locating where things fall on the eye and so forth like that. So it's kind of form and function integrated together.
Do they have any predators?
Very a few. I mean, when they're tenorals, when they've just emerged, they can fly, but the cuticle and the wings are not fully cured, so to speak, and so they're not quite as high performance. And so then things like birds and spiders can prey among them. But once they're mature adults or healthy mature animals, I mean, in general, not really. I mean.
Because I'm wondering what happens if you get an animal that has, you're ignoring the little life cells, which is probably where a lot of the integration is going on. And the question is, if the animal has conflict, what do? If it has predator up ahead.
Yep. Well, so I think the conflict they get is more so is too many prey. So I think that they don't like. It's a weird. It's a very fragile system in some ways. So like we also study prey capture and salamanders, and these guys are amazingly robust. You can put them in any lighting condition you want, in any comfort level, and they'll just kind of catch these things. And dragonflies, they like textureless blue sky, warm temperatures, very few prey. I mean, they like a lot of prey, but they don't like a cloud of prey above them. They like to kind of see one or two things, and you have the sense if there's like 20 targets flying around, the system doesn't work as well because it's hard to discriminate all that stuff. And so they seem, and in the summer, that's the average condition, so it's not hard to attain that. But if you have a rainy week, all the dragonflies die off. And more come out of the ponds.
So if the head can move, it does. I guess you're talking about these neurons being target-selective neurons, but the movement of the body is sort of independent of the movement of the head. So, since you're not tracking with the head,
well, we're working on doing that. So the first order study we'd like to do with the work Reid and I have been doing is, so what's been done is head fixed recordings of these neurons to a visual stimulus. So you kind of know you have a rough sense of this forward transfer function. They have receptive fields in different places and directions. The first thing we'd like to do is sort of a body triggered version of, so the neuron spikes, and what does the body plane do? Does it turn left, right, up, down, right? And so for that, we don't need the head, but it would be greatly assisted with the head because that's where the receptive fields of these neurons are. So the head dictates what the neurons are seeing, and they actually foveate on the target. So like when they're flying like this, they're tracking the targets with their head and moving it smoothly. And so, the second order version of this that we spent a lot of time working on is a way to measure real-time head and wing states. So we can actually, in free flights, we can reconstruct that. And we do that with sort of a retroreflective tracking system we've been developing. And so we can put little markers on the head and then reconstruct a three-dimensional orientation of the head and then go back. Since we have a controlled environment, we can figure out what they see in terms of background and foreground. I mean, that's what we'd like to do. So this is kind of, but it's obviously difficult to do all this.
the head movement is always smooth. It doesn't do this kind of nystagmus, right?
Well, nobody really knows, but the extent to which Olberg has measured this stuff, very close range versions of dragonflies doing movements that are pretty smooth in flight.
So there's also work on territorial air battle between dragonflies, and it's similar to guidance law, like the missile.
Yes.
But what you're saying is when they're capturing a prey, this kind of guidance occurs only in the azimuth, in the elevation direction.
It seems to, yeah. In azimuth, they do, rather than proportional navigation, they do something much more like pure pursuit, where they just try to point themselves right at where the fly's going, and they end up in a tail-chasing dynamic. And so I wouldn't want to say they absolutely do this guidance law in one and this in the other, but if you just qualitatively look at the data, there's a definite difference. And I mean, you never see them go, you never see them go head on to the prey, right? So that never happens. And it could be because the relative speed is very fast and it's much harder. It could be because they're much easier to see, because insect eyes kind of tend to have a field of view like this. And so things like down on the ground in front of you are very easy to see in terms of motion and avoid, whereas things behind you is where your blind spot is. So it could just be tactical. But qualitatively, they definitely don't do the same things in these kind of two celestial coordinate systems.
groups that study neurotelemetry and neural systems have been working on things like spike sorting circuits, where you would try to identify the identity of a certain neural spike prior to transmission, prior to storage. To what extent do you think in a system like this would be useful? Because you wouldn't be able to necessarily always be able to check the quality of the sorting and so forth. Is this the kind of system that would
I think it's not so useful.
Not so useful.
It depends on your question. I think for prosthetics or simple control theoretic, applications of recording from many neurons to make an actuator do something, it's super useful. But for what we're doing, we must know the neurons we're recording from, and that requires. Clearly, if you could put all the logic into an IC and put it on the animal, and it did that, and it did the same thing I'm going to do in my own analysis to figure it out, it would be equivalent. But what I've normally seen is just things that are much simpler. Schmidt triggers and other things that give you peaks and widths and other amplitudes, and that I think we would not have enough confidence in. Or a better way to put it would be, I think there's a feeling that it would be easier to build something with more bandwidth or more channels that you'd have perfect confidence in than to do that and you'd kind of be worried that the data wasn't quite right. So that's, again, this very specific thing, but these neurons are pretty easy to find, and you kind of know when you have them, and so we can do stuff like dial in a neuron in a restrained animal and lock stuff down and be confident that we have the same, maybe as confident as we are in the restrained setup. So, but if it could be done really well, that would be great. But I think it's tough to, in MATLAB we do pretty sophisticated stuff, so it's hard to, put that on the animal's head.
One thing we've thought about, is like every time you identify a spike, which is a simple threshold that you set, and you set a snapshot. But then you just go, well, how do you handle a worst case? Because all the interesting stuff, like with DCMD and the locus, all the interesting stuff, when interesting stuff starts happening, you get a lot of activity, and so you have to be able to handle the worst case, which doesn't really solve the problem at all.
It's like a robustness issue. Though, I would love to, if somebody made it, we would certainly try and we'd love to use it. But I guess what I mean is more, if you sort of put two things on the table and said, what do you want, spike sorting or 10 megahertz of many channels, we would take the latter one.
Next year's versus.
Yeah.
Okay, well, very good questions. Thanks.